In November of 2024, astronomers announced they'd found something that shouldn't exist. A black hole sitting in the early universe, feeding on surrounding matter at 40 times the maximum rate physics was supposed to allow. Headlines called it impossible. Scientists called it a serendipitous discovery that could finally explain one of the biggest unsolved mysteries in modern astrophysics. And then, 5 months later, a second team of researchers went back, checked the math more carefully, and found that a huge chunk of that impossible number had actually been an illusion, created by something as mundane as cosmic dust. This is the real story of LID 568, the fastest feeding black hole ever documented in the early universe, why its extreme growth rate briefly appeared to break the laws of physics, and what happened when scientists went back to check their own extraordinary claim. Let's start with the specific problem this discovery was trying to solve, because it's one of the genuinely open, difficult questions in modern astrophysics, and it's been sitting unresolved for years. Scientists have spent decades puzzled by how supermassive black holes, objects containing millions or even billions of times the mass of our Sun, managed to grow to such staggering size within the first billion or 2 years after the Big Bang. Standard models of black hole growth describe a relatively slow, steady process, matter gradually spiraling inward and accumulating over enormous stretches of cosmic time, governed by well-understood physics that places real limits on how quickly that growth can happen. Under those conventional models, building a black hole containing millions or billions of solar masses should simply take longer than the age of the universe allowed, at the specific point in cosmic history where Webb keeps finding these objects already fully formed. But the James Webb Space Telescope has repeatedly found supermassive black holes already fully formed at points in cosmic history far too early for that slow, steady process to have had enough time to work. This has become one of the signature puzzles of Webb's entire mission, showing up again and again across multiple independent observations of the early universe, forcing astronomers to seriously consider that some additional, faster growth mechanism must be at work, something beyond the patient, gradual accumulation described in older textbook models. Something, somewhere, has to be helping these black holes grow dramatically faster than conventional models predict. And finding direct evidence of exactly what that something actually is has become one of the most actively pursued questions in the field, discussed constantly at conferences and referenced in paper after paper trying to explain Webb's growing catalog of impossibly early, impossibly massive black holes. That's the exact context in which LID 568 entered the story. A research team led by Heewon Soo at the International Gemini Observatory and NSF's NOIR lab was examining a set of galaxies originally identified through the Chandra X-ray Observatory's Cosmos Legacy Survey, a long-running, wide-field study of distant galaxies conducted in X-ray wavelengths, using the James Webb Space Telescope's exceptional infrared sensitivity to study them in far greater detail than had previously been possible. One particular black hole in that dataset, later designated LID 568, immediately stood out because of its unusually intense X-ray emissions, a signal strong enough to draw the team's specific attention for closer follow-up observation using Webb's more precise instruments. What made LID 568 especially interesting from the outset was something Sue herself noted directly. Most of the early universe black holes Webb has detected are very faint or even completely undetectable in X-rays. LID 568 was different. It was bright, and that brightness was the first clue that something genuinely unusual was happening there, something worth dedicating additional, valuable telescope time to investigate more closely. Observed as it existed roughly 5 billion years after the Big Bang, LID 568 turned out to be relatively small by supermassive black hole standards, with a mass of about 2 million times that of our Sun, modest compared to some of the far larger supermassive black holes found at the centers of galaxies today, some of which weigh in at billions of solar masses. But the light being emitted by the material actively falling into it, the black hole's accretion disk, was enormously brighter than a black hole of that specific mass should have theoretically been able to produce. That mismatch, a comparatively modest mass, paired with an extraordinarily bright glow, was the central puzzle driving the entire follow-up investigation. And it's exactly the kind of anomaly that tends to catch the attention of an entire research field once it's published. Using Webb's near-infrared spectrograph in a specific mode called integral field spectroscopy, which captures both an image and a detailed light spectrum for every pixel in the frame simultaneously, Sue's team was able to study not just the black hole itself, but the powerful outflows of gas surrounding it, streams of material being blasted outward from the extreme environment near the black hole's edge. Those outflows turned out to be unlike anything the team had previously documented in an object of this kind, remarkable both for their speed and their physical scale, extending outward from the black hole in a way that suggested genuinely violent, energetic activity happening in the immediate surrounding environment. By carefully measuring the speed and physical size of those outflows, the team calculated that LID 568 appeared to be consuming matter at a rate more than 40 times higher than what's known as the Eddington limit, a fundamental threshold in astrophysics, named after the physicist Sir Arthur Eddington, who first derived the concept mathematically in the early 20th century, describing the maximum rate at which a black hole should theoretically be able to feed. The basic physics behind that limit is straightforward once you break it down. As material falls toward a black hole, it heats up dramatically and emits radiation, and that outward-pushing radiation pressure eventually counterbalances the black hole's inward gravitational pull, effectively capping how quickly it can keep consuming new material, without simply blowing that material back away from itself before it can actually fall in. Exceeding that limit, entering what's called super Eddington accretion, means a black hole is somehow continuing to feed dramatically faster than that radiation pressure should theoretically allow, if only for a limited period of time, before the imbalance presumably corrects itself one way or another, either by the black hole finding some way to vent the excess energy, or by the feeding process eventually choking itself off entirely. Sue and her colleagues proposed that these extreme gas-driven outflows might actually be functioning as a kind of pressure release valve, allowing excess radiation energy to escape the system efficiently enough that the black hole could keep pulling in matter at a rate that would otherwise be self-limiting. Their results suggested that a significant portion of LID 568's entire observed mass may have been gained during a single, extraordinarily rapid feeding episode, essentially one dramatic cosmic meal responsible for a huge fraction of the black hole's total growth. If that mechanism turned out to be real and repeatable across other similar objects, it offered a genuinely compelling explanation for exactly the kind of impossibly fast early supermassive black hole growth that had been puzzling astronomers throughout Webb's entire mission, potentially resolving one of the field's most stubborn open questions in a single elegant stroke, and giving theorists a genuine, physically grounded mechanism to build future models around. The finding, published in the journal Nature Astronomy in November of 2024, generated exactly the kind of excitement you'd expect from a result suggesting black holes could occasionally dramatically break their own theoretical feeding limit. It offered astronomers a genuine physical candidate mechanism, finally, for solving one of the field's most persistent open puzzles. Sue herself described the result as serendipitous, adding a new dimension to the team's understanding of the system and opening exciting new avenues for further investigation. Coverage of the discovery spread quickly across science outlets, often using language like impossible and defying physics. Language that, while dramatic, wasn't entirely unreasonable given how extraordinary the original 40 times figure genuinely was, if it held up under further scrutiny, which is exactly the qualifying condition that turned out to matter so much just a few months later. But here's where the honest version of this story becomes more interesting and more scientifically important than a simple, permanent record-breaking headline. In April of 2025, roughly 5 months after the original announcement, a separate team of researchers went back to re-examine the data behind LID 568's extreme feeding rate and found a significant problem with the original calculation. The issue centered on cosmic dust and specifically on how much that dust was dimming and distorting the light reaching Webb's instruments from this heavily obscured object. As the researchers explained, dust absorbs and scatters light, significantly reducing the amount and altering the character of light that ultimately reaches our telescopes from a source like LID 568. For an object this thoroughly obscured by surrounding dust, properly correcting for that dust extinction turns out to be absolutely critical to getting an accurate final measurement, since failing to account for it can make an object appear dramatically fainter, or its emitted light dramatically different in character than it truly is at the source, which in turn can badly skew any calculation built on top of that raw, uncorrected data. Youngshin Im, director of the research center involved in this follow-up study, emphasized that point directly. For a heavily dust-obscured object like LID 568, correcting for dust extinction properly isn't optional. It's essential to arriving at an accurate answer at all. One of the specific strengths of Webb's infrared sensors, ironically, is their ability to peer through exactly this kind of dense, obscuring cosmic dust more effectively than most previous instruments could manage, which is part of what made LID 568 detectable and studable in this level of detail in the first place. But that same dust still had to be properly, quantitatively accounted for in the final calculations and the original analysis. The follow-up team concluded hadn't applied that correction with sufficient care, leading directly to an inflated final figure for the black hole's feeding rate. Once that more careful dust correction was applied, the picture changed substantially. Rather than feeding at 40 times the Eddington limit, the corrected analysis found that LID 568 is actually accreting matter at a rate broadly consistent with the Eddington limit itself, not dramatically exceeding it the way the original announcement had suggested. The initial dramatic overestimation, the researchers concluded, had been caused specifically by that uncorrected dust extinction skewing the earlier measurement toward a far more extreme result than the underlying physical reality actually supported. That correction doesn't mean the entire original discovery was worthless, or that the story ends in simple disappointment. It means something more genuinely instructive about how real science actually works. LID 5668 remains a real, fascinating, actively studied object, an early universe black hole with unusually powerful gas outflows and genuinely interesting accretion behavior, still relevant to the broader puzzle of early supermassive black hole growth. What changed wasn't the existence of the object or the value of studying it. What changed was the precision of one specific, headline-grabbing number. Once a second team applied more careful methodology and caught a source of measurement error the original analysis hadn't fully accounted for. That's genuinely how good science is supposed to work. And it's worth appreciating, rather than treating as some kind of embarrassing walkback. A team makes an extraordinary claim based on real data and legitimate methodology, published through the normal peer review process in a respected journal. Other researchers, specifically because the claim was extraordinary enough to deserve careful scrutiny, go back and check it independently, applying additional corrections and catching a specific source of systematic error that the original team's methodology hadn't fully addressed. The final corrected picture is less dramatic than the initial headline, but it's more accurate, and the entire community's understanding of exactly how to study heavily dust-obscured black holes in the early universe improved as a direct result of that correction process. A benefit that extends well beyond just this one specific object, informing how future observations of similarly obscured objects will be analyzed and corrected going forward. It's also worth being clear about why this particular correction doesn't actually resolve the broader mystery that made LID 568 exciting in the first place. Even with the corrected, more modest feeding rate, astronomers still don't have a complete, settled explanation for how supermassive black holes manage to grow as large as they do, as early as they do in the history of the universe. The original Super Eddington hypothesis, brief periods of extreme, rule-bending accretion helping explain rapid early growth, remains a genuinely active area of theoretical and observational research. Discussed directly in ongoing scientific literature examining multiple early universe black holes, some of which do appear to sit right at, or potentially beyond, the boundary the Eddington limit describes, according to broader theoretical modeling work published alongside and after the LID 568 correction. Separate research has continued examining other candidate objects for evidence of this same Super Eddington behavior, some of them showing signs consistent with genuinely exceeding the theoretical limit, even after applying the same kind of careful dust correction that revised LID 568's figures downward. LID 568 specifically no longer serves as the clearest, most extreme example of that phenomenon, but the underlying question it was originally recruited to help answer remains genuinely open. And researchers continue actively searching for other candidate objects that might demonstrate the same Super Eddington behavior more robustly, using exactly the lessons learned from this specific correction to avoid repeating the same measurement error elsewhere. What makes this story worth telling honestly, including the correction, is that the corrected version is actually more valuable than the exaggerated one would have been if it had simply gone unchallenged. A permanently uncorrected claim of 40 times, or the wildly inflated 10,000 times, sometimes attached to viral retellings of this story online. A figure with no basis in any actual published research on LID 568 or any other known black hole would have left a false, misleading figure sitting in the public record indefinitely, actively distorting genuine scientific understanding of how black holes really behave and how fast they can plausibly grow even under the most extreme, rule-bending circumstances physics allows. Instead, what actually happened, real scientists catching a real measurement error, applying more careful analysis, and publishing a corrected result in the same rigorous, peer-reviewed process that produced the original claim, represents science functioning exactly the way it's supposed to, self-correcting, transparent about its own uncertainty, and willing to revise even a genuinely exciting, headline-worthy claim once better methodology reveals a more accurate answer. There's a broader lesson here too, one that applies well beyond this single black hole. Extraordinary claims in astrophysics, especially ones involving objects at the very edge of our observational capability, obscured by dust, sitting billions of light years away, observed using instruments and techniques still being refined and improved, deserve exactly this kind of ongoing scrutiny and willingness to revise. That's not a weakness of the scientific process. It's the entire point of it. The first announcement of a discovery is rarely the final word, and treating it as such, whether by inflating the numbers further for a viral headline or simply repeating the original figure without acknowledging the correction, does a disservice to the actual, careful, sometimes messy work scientists do to get closer to the truth work that often unfolds over years, across multiple papers, multiple research teams, and multiple rounds of correction and refinement before a genuinely stable, reliable answer finally emerges. If this story helped you understand not just what Webb found, but how science actually corrects itself when a big claim doesn't fully hold up, hit subscribe. Because the real process behind these discoveries is often more interesting than the first headline ever lets on.